All right, welcome back in the channel. Today we are selecting Ethereum modified Merkle Patricia Trie. This is a very important data structure used in Ethereum because if we talk about Ethereum, it's like a global computer. You need to have a global data structure where you want to store all types of actions that happen on Ethereum network, whether it's a simple amount transfer from one Ethereum account to another Ethereum account, or it's any interaction with the smart contract. So all things are stored in this global state. That's the data structure behind that state is Merkle Patricia Trie, and in Ethereum it has been slightly modified. That's why we call it as Ethereum modified Merkle Patricia Trie. In this video we are basically LLM-fying things, right? So today we will LLM-fy Ethereum modified Merkle Patricia Trie. So starting from what you can do with this visualizer, you can have overview, the construction, the node types, and encoding. I will provide the link in the description where you can easily walk through each and every step of this data structure. But for this video, I will try to explain the construction, the basic construction of Ethereum, state trie here. So we'll start with the construction, and we will start with the full initially. If we are storing the data about a single account, so it will look like this. So this is the account, externally owned account. This is the data inside the nonce, and we will be seeing what will be the structure of the trie when we insert the data about a single account, right? So if we look, just hiding this here, I will bring this here leaf. So when we have only one account, so this obviously as a tree, it will still be as a leaf. So what is the structure of the leaf? We have already seen there are three types of nodes. If we talk about one, we have the leaf node, we have the extension node, and we have the branch node. Since leaf and extension are very similar in structure because they have prefix and the value in both of these nodes, so we need kind of a differentiator. So for that we use prefix, and for leaf node we have dedicated prefix. So we'll see here we have 2, right? So if you have even number of nibbles, then you put 0 with the prefix, so that total you have even number of nibbles in total. But in case of if you have odd, then we are using prefix for that, so we don't need to put any padding, right? So for even we use padding, for odd we don't use padding. But for extension nodes, we have different prefix, right? And the same rule goes there. If there is odd number of nibbles, then we don't use any padding. If there is even, then we use padding. So how the data will look like in Ethereum, we have this. And then our LP encoding will be the encoding of the Ethereum data itself with the prefix and the padding itself, right? So it's very simple for the single account. Now the complexity grows as we put more and more Ethereum accounts into this global state trie. Right. So another account we have here is this one. Now, if we look at, there is, prefix A7 is same in this. So we are forced to use split and change the structure from leaf. We need to use the branch now. And then, of course, if we have common prefix, we have to use extension. Extension also has prefix and the value. The prefix we have already seen, there will be specific prefix for the extension nodes, right? And then the value is basically the hash of the next node that it is pointing. Here, obviously, it's pointing to the branch node. Then branch node has a unique structure. It has 17 slots. We have 16 slots for 16 characters of hexadecimal numbering, right? 0 to F. Then we have the value. Sometimes have the value of that node or that account in the branch node. But for other slots, 0 to F, they will point to, basically, they have this, hash of the nodes they're pointing, right? So here I'm explaining, like, now we have two nodes with the common prefix, right? If we look at what we are seeing here is, this is the extension node, and extension node have two types of two prefixes. If it is even, then you have 0 extension because the nibbles are even, and we must use the padding 0 again to make it like even numbered nibbles, right? So if we use prefix, then we have shared nibbles A7, we have to put padding 00, then we can directly RLP encode it, right? If we have odd, then we will prefix as 1, and we don't use padding because that odd things will be there in shared nibbles, plus 1 prefix, it will be even, right? So it's clear now. For leaf nodes, we have 2 prefixes, depending upon whether the nibbles or the data nibbles are the prefix. We can say the path has odd or even nibbles, right? If it is odd, then we use only prefix. If it is even, we use with the padding. And in case of extension node, if it is even nibbles, we use 2 as prefix plus padding. In case of odd nibbles, we use 3 as prefix and nothing as padding. So it goes with the extension node. If it is in the even number of shared nibbles, then we use 0 as prefix and we use padding as 0 as well, right? In case of odd number of shared nibbles, we use prefix 1 but no padding. Nodes here, right? And the two nodes will be having the links at their respective index slots in the branch node. Since if you look at the what was the account A71 and A77 branch node, you will get like this. So you see at 1 index and at 7 index we have exactly the hash of the child nodes they point to, right? So finally we have at the end we have 2 leaf nodes now, right? Let's explore a few accounts more so that because we want to see the complexity, right? So if you look here, I want to try to, if anything, if suppose there is an account which has all the nibbles same but only the last nibble is different, suppose that comes at 4 and 5, we can have directly a link of that node here and it will be treated as a link, its link, right? So let's see what will happen. Here we go. We have this F account. If we look at this, what was the account? See, we were having A7F, so it is only differentiating at F. So we can have a direct node standing, just connected with the branch node. So I will just complete it here because I want you to explore this visualizer so you can get used to like the complexity that it grows. So I will quickly walk through with other sort of things when next nodes will come, how your Ethereum state trie gets modified, that encompasses like everything is getting stored in a slight action, slight transfer of value on Ethereum or DeFi interaction with the smart contracts and all. So here if we have another node, like see we have the 4th node coming in this one. The nibbles between account 2 and account 4 are now having this, so that means we must bring it here, just closing it down. Now we have this, but there is A7FF, right? A7FF, yeah, A7 then they have like the shared nibbles more, right? So the third leaf that was present exactly at the 7th second leaf, of course, will be just broken down into the extension, then the branch, and then the corresponding 2 leaves. If you look at here, because now we have the shared 7 3 leaf, because A7 final differentiating nibbles as 3 as 9 will be having those leaf nodes here. So this is of course the leaf 4 and this is the leaf 5 that we have. So you have to just explore the visualizer to get all sort of details once for all, because this is the type of a structure that when we usually start first time looking and diving deep into the Ethereum, you find it very difficult how Ethereum modified Merkle Patricia Trie is just storing all sort of things, and how Ethereum account acts as a key, and how it's quickly balance from the Ethereum trie very quickly. So this is the optimized data structure that is that is like doing job for us at the background. So thank you very much for watching the video, and I will highly encourage you to just subscribe the channel LLM because here what we do is just basically we are LLM the concepts to get more simpler, more engaging, and more interactive understanding of the complex topic.